Imagine if someone pressed pause on the global hydrogen story and asked a hard question. What actually happened to all those world's first green hydrogen plants, zero-emission truck fleets, and gigawatt-scale electrolyzer hubs that were supposed to change everything by 2030? For a few years, it felt like hydrogen was everywhere, on conference stages, in government roadmaps, in corporate strategy decks. It was hyped as the molecule that would decarbonize everything electricity couldn't touch. But between 2024 and 2025, reality hit. Projects were canceled. Costs didn't come down fast enough. Customers refused to sign long-term contracts. Some of the loudest early movers collapsed in very public ways. And yet, at the same time, a quieter group of companies and projects has been moving forward, learning from the wreckage, and showing what a grounded, disciplined hydrogen strategy actually looks like. If you zoom out today, you don't see a simple success or failure story. You see an industry being forced to grow up. In this video, we're going to walk through that journey. We'll look at what went wrong with the first wave of green hydrogen and fuel cell hype. We'll dig into the economics, the policy missteps, the technical problems, the demand gap, and a few very high-profile failures like hydrogen trucking. But we're also going to look at what's working: real projects with real off-takers, co-located value chains, modular growth, pragmatic, color-flexible hydrogen strategies, and a much more sober understanding of where hydrogen truly adds value. By the end, you'll have a clear picture of what hydrogen's adult phase actually looks like, and what it means for investors, developers, and policymakers as we head toward 2030. Let's start with the part a lot of early adopters tried to hand-wave away: the economics. Green hydrogen, hydrogen produced by electrolyzing water using renewable electricity, was pitched as the clean replacement for gray hydrogen from natural gas. The narrative went like this: costs for solar and wind will keep falling, electrolyzers will ride a fast learning curve, subsidies will bridge the early gap, and by the early 2030s, green hydrogen will be competitive almost everywhere. The problem is that the real world didn't follow that script. Even as electrolyzer prices fell on paper, the total cost of green hydrogen stayed stubbornly high once you accounted for everything that actually matters in a project. The price of renewable electricity, grid connection costs, land, water treatment, balance of plant equipment, compression, storage, and transport. Industry analysis and executive commentary converged around a simple, uncomfortable fact. In most markets, green hydrogen has been roughly 2 to 3 times more expensive than conventional gray hydrogen. The International Energy Agency's Global Hydrogen Review 2025 really drove this home. Despite all the announcements, almost all hydrogen demand today still comes from traditional uses like oil refining, ammonia, and methanol production, and almost all of that hydrogen is still fossil-based. Low-emissions hydrogen, whether it's green or produced with carbon capture, accounts for less than 1% of total supply. After years of conferences and roadmaps, the physical molecules being used in the global economy look almost exactly like they did a decade ago. Governments and companies assumed that generous subsidies, carbon prices, and rapid cost declines would quickly close the gap. Instead, high power prices in many regions, rising interest rates, and inflation in supply chains pushed many green hydrogen business models deep into the red. The hype collided with the bill, and that led directly to the second structural problem: the demand gap. A lot of early green hydrogen projects were built on a quiet assumption that if they created a huge supply, demand would somehow appear. The phrase, "build it and they will come," was never said out loud in official project documents, but it was baked into many models. In reality, industrial customers are brutally rational. A steel company considering hydrogen-based direct reduced iron, a refinery thinking about replacing gray hydrogen, a trucking operator evaluating fuel cell vehicles. None of them are going to make billion-dollar capital decisions on the back of vague promises and volatile costs. They want long-term, bankable contracts at prices that make sense against their existing fuels and processes. They want regulatory clarity. They want infrastructure. And if those pieces aren't there, their default answer is simple: not yet. The IEA's tracking data shows exactly that. Hundreds of gigawatts of low-emissions hydrogen capacity have been announced on paper, but only a small fraction has actually reached final investment decision. The reasons are always the same: uncertainty about future demand, unclear regulation, and missing infrastructure. Offtake deals, which are the lifeblood of project bankability, actually slowed in 2024, dropping from 2.4 million tons per year of hydrogen in 2023 to about 1.7 million tons per year in 2024, and most of those weren't even fully firm commitments. By 2024, only around 7% of global announced project capacity had reached a firm FID, and a large portion of that was concentrated in China, where state-driven industrial policy and large renewable bases are driving projects ahead while much of the rest of the world hesitates. Policy design made things even harder. On one level, hydrogen is a heavily policy-driven market. Subsidies, tax credits, definitions of clean, and grid connection rules can make or break a project. In Europe, the intention was good. Make sure that green hydrogen really is green by requiring additional renewable capacity and strict hourly matching between electrolyzer use and clean power generation. In practice, those rules added enormous complexity and cost. Developers had to show that every hour of electrolyzer operation was backed by new, dedicated renewable output, rather than generic grid electricity. Industry groups warned that such rules could increase hydrogen production costs by roughly 1/3 and accelerate stack degradation, because electrolyzers would be forced to ramp up and down constantly. Major electrolyzer manufacturers went so far as to publicly urge EU policymakers to soften the rules, pointing out that factories were standing idle while projects waited for workable frameworks. In the United States, the supporting mechanism looked simpler: a production tax credit under Section 45V of up to $3 per kilogram of clean hydrogen. On paper, that's powerful enough to flip project economics. But long delays and uncertainty around the Treasury's interpretation of what counts as clean hydrogen created a fog that developers couldn't model through. For investors and lenders, waiting for detailed guidance became a recurring reason to pause or cancel projects. Legal analyses started to document a pipeline of delayed or abandoned projects where uncertainty about 45V eligibility was a central factor. The result, on both sides of the Atlantic, was a strange paradox. Strong political support for hydrogen on the surface, but so much complexity and uncertainty beneath it that capital struggled to move. While all this was happening, technical and infrastructure realities quietly undermined some of the more optimistic narratives. Scaling electrolyzers from a pilot system to a 100 or 200 megawatt project is not just a matter of stacking more modules together. When you feed an electrolyzer with intermittent wind and solar, you introduce fluctuating loads, temperature swings, and complex control challenges. Laboratory studies had already indicated that PEM electrolyzers degrade faster under highly variable power input. Operators doing early large-scale deployments confirmed this. Performance in steady test environments did not automatically translate to robust performance in real-world grid conditions. Stack lifetimes, efficiency at partial load, and maintenance requirements all turned out to be more demanding than the sales brochures suggested. On the downstream side, the infrastructure story was equally sobering. Hydrogen is expensive to store and move. Compressed gas requires high-pressure vessels and compressors. Liquid hydrogen needs extreme refrigeration, continuous boil-off management, and careful safety engineering. Without a dedicated pipeline network, most projects rely on trucks for transport, which is slow, costly, and inefficient at scale. Analysis from industry groups and technology providers has repeatedly flagged storage, compression, and transport as some of the largest obstacles to scaling a hydrogen economy. In effect, early green hydrogen developers were trying to build an entire value chain from scratch. Renewable generation, conversion, storage, transport, and end use, often in regions that lacked supporting infrastructure. Every link in that chain introduced risk, delay, and cost overruns. If there was one segment where the clash between hydrogen's public narrative and its real-world performance was impossible to ignore, it was heavy-duty transport. Hydrogen trucks became a powerful symbol of the future of freight. One company in particular, Nikola Corporation, positioned itself as the vanguard of a hydrogen trucking revolution. But by February 2025, Nikola had filed for Chapter 11 bankruptcy. Court filings and industry reports painted a picture of unsustainable cash burn, difficulty scaling manufacturing, vehicle recalls, and far weaker demand for fuel cell trucks and hydrogen fuel than the company had projected. Earlier leadership scandals had already damaged its credibility. By mid-2025, more than 100 hydrogen trucks from Nikola's inventory were being auctioned off, not as fleet-transforming assets but as distressed equipment. Commentators observe that even if someone wanted to operate those trucks, the hydrogen fueling network in the United States was so limited that real-world operation would be extremely difficult. It became a cautionary tale of what happens when aggressive marketing and ambitious promises run ahead of infrastructure, economics, and trust. The retreat wasn't limited to startups. Some of the world's biggest industrial players faced their own reckoning. In early 2025, Air Products announced that it would exit 3 major U.S. green hydrogen projects after a board-level review, taking more than $3 billion in write-downs. One of those projects, a 35-ton-per-day liquid hydrogen plant in Messina, New York, collapsed after changes in tax credit rules suddenly made its hydroelectric power ineligible. A regulatory rug was pulled, and the economics collapsed with it. In the United Kingdom, BP abandoned its flagship H2 Teesside blue hydrogen project at a former steelworks site. The land is now planned for a massive AI data center instead. BP acknowledged that the hydrogen project had become incompatible with the new data center, and that weakening industrial hydrogen demand from local offtakers further undermined the case. Even Iberdrola, one of Europe's most committed green hydrogen developers, cut its 2030 target for green hydrogen production from 350,000 tons per year to 120,000, citing delays in government funding and adverse market conditions. Their CFO summed it up bluntly. Hydrogen was the only target they were scaling back, not because they lost faith in the technology, but because the economics and subsidies weren't there yet. So that's the autopsy. High costs, a demand gap, policy friction, technical and infrastructure challenges, and a few high-profile failures. All of that forced a sharp reset. But that's not where the story ends. The more interesting question is, who survived this storm, and what are they doing differently? If you look closely at the projects that are actually operating in late 2025, a very different hydrogen strategy emerges. Quieter, smaller on paper, but far more robust in reality. These projects have a few key things in common. First, they start from real, existing demand rather than speculative new use cases. A prime example is the Puerto Llano Green Hydrogen Project in Spain, a collaboration between Iberdrola and Fertiberia. Instead of building a giant hydrogen hub in the middle of nowhere and hoping someone would buy the output, they co-located everything. A 100-megawatt solar farm, a battery, and a 20-megawatt electrolyzer sit next to Fertiberia's ammonia plant. The hydrogen flows directly into an existing process, replacing part of the gray hydrogen the plant was already using. No long-distance transport, no new end-use sector, no "if you build it, they will come" fantasy. Just decarbonizing an incumbent demand with a known offtaker under contract. Second, successful projects aggressively minimize distance. Every kilometer that hydrogen has to travel adds cost and complexity. The projects that are moving ahead tend to integrate generation, conversion, and use on the same site or within the same industrial cluster. In some cases, this means hydrogen is produced right next to a refinery, an ammonia plant, a methanol plant, or a data center. Some industrial clusters are planning shared infrastructure, pipelines and storage that serve multiple users in one hub. But the underlying logic is the same. Shrink the physical supply chain as much as possible. Third, they grow modularly instead of chasing instant gigawatt-scale headlines. Electrolyzers are inherently modular. The smarter developers treat them like industrial equipment that needs to be proven at a smaller scale before being deployed in massive arrays. That means starting with 10, 20, or 50 megawatt phases, getting the engineering and operations right, and only then expanding in repeatable blocks. It also means designing project plans where phases can be added as demand grows and as costs improve, instead of betting everything on one huge all-or-nothing first phase. Fourth, they are brutally honest about the cost of electricity. Because electricity is the single largest input to green hydrogen, serious developers are locating projects where they can access very cheap, very clean, and relatively stable power. That often means pairing projects with high-quality wind or solar resources in sparsely populated areas, or with existing nuclear and hydro assets. In China, for example, many new hydrogen projects are linked to giant renewable bases in the desert northwest, where land and resource quality keep the levelized cost of electricity low. In the United States, developers are gravitating toward places like Texas, New Mexico, and certain parts of the Midwest. The IEA has been clear that reaching hydrogen costs in the $1 to $2 per kilogram range will require very low power prices at high capacity factors. Projects trying to make green hydrogen work in high-cost or coal-heavy power systems are increasingly being shelved as uneconomic. Fifth, the more pragmatic players are moving away from ideological battles over hydrogen colors and embracing diversified production pathways. In practice, that means mixing hydrogen from electrolyzers with hydrogen from natural gas plus carbon capture, biogenic sources, or even transitional gray sources in some applications. For large industrial users, this portfolio approach can deliver decent emissions reductions today while preserving flexibility as cleaner options scale up. Some data center concepts, for example, use fuel cells running initially on natural gas or mixed hydrogen streams with a clear roadmap to pure green hydrogen as supply increases. Startups in the data center space have openly said they are buying a mix of gray, blue, and green hydrogen today, while committing to eliminate gray within a defined time frame. This kind of staged decarbonization is messy but realistic. Companies that insist on 100% green hydrogen from day one, in a world where that supply barely exists, often find themselves unable to start at all. Sixth, the winners are focusing hydrogen on the niches where it truly shines. The IEA's own tracking shows that outside of traditional refining and basic chemicals, new hydrogen demand is emerging mainly in places where alternatives are weak. Biofuels production, sustainable aviation fuels, and certain high-temperature industrial processes. In road transport, batteries have taken over passenger cars and are rapidly gaining ground in light commercial fleets. Hydrogen still has a role in specific heavy-duty applications, forklifts and warehouse equipment with tight space constraints, certain long-haul trucks operating in fixed corridors with centralized refueling, and backup or prime power where 24/7 uptime and high power quality justify a premium. Plug Power's fuel cell forklift business is a good example. In large logistics centers, these forklifts refuel in a few minutes instead of sitting on a charger, avoid the need for dedicated charging rooms, and maintain consistent performance over multiple shifts. In those environments, the total cost of ownership can actually favor hydrogen, even if the fuel itself is more expensive than electricity. Similarly, in backup power for data centers, solid oxide fuel cells running on natural gas today, and potentially hydrogen tomorrow, are being adopted because they offer higher efficiency and cleaner operation than diesel generators while delivering the reliability hyperscale data centers demand. All of this points to a very different way of thinking about hydrogen as we move toward 2030. The mature hydrogen strategy is not hydrogen everywhere. It's hydrogen in specific high-value niches where its unique properties matter. As a feedstock where there is no easy substitute. As a high-temperature heat source where electrification is difficult. As an energy carrier for long-duration storage. And as a fuel in constrained, heavy-duty or critical power applications. It's also hydrogen that is produced close to where it is used with cheap, clean power, under contracts that fix the economics for both supplier and offtaker. So what does that mean if you're a developer, investor, or policymaker trying to decide whether to lean into hydrogen or step back? It means designing projects backwards from the end-use customer, not forwards from the technology. Start by asking, who is the offtaker? What are they using now? What are their constraints and alternatives? What price and risk profile would make them actually sign a long-term contract? Only after that do you decide whether hydrogen is the right tool, and if so, what configuration of electrolysis, storage, and delivery makes sense. It means only building where your fundamental inputs, especially electricity, are favorable. No amount of branding can overcome bad physics and expensive power. It means starting small, proving performance under real-world conditions, and planning for maintenance and degradation instead of assuming the equipment will run like a perfect black box. And it means putting hydrogen in competition with batteries, efficiency improvements, and direct electrification, not in a separate silo where every problem magically has a hydrogen answer. The painful years of 2024 and 2025 didn't mark the end of hydrogen. They marked the end of hydrogen's adolescence. The industry has been forced to confront the gap between the story it told about itself and what it could actually deliver on the ground. A lot of press releases didn't survive that confrontation. Some early high flyers didn't either. But in their place, a more disciplined, more credible wave of projects is taking shape. Projects with real offtake, realistic scales, clear economics, and phased build-outs. Policymakers are starting to adjust frameworks to be more workable without abandoning environmental integrity. Investors are focusing less on hype and more on cash flows and risk management. Hydrogen will not decarbonize everything. It won't replace batteries in your car or heat pumps in your home, but it can be one of the critical pillars in cleaning up heavy industry, chemical production, long-distance fuels, and parts of the power system. The companies that underpromise and overdeliver, that stay disciplined on economics, that integrate hydrogen smartly into the wider energy system, those are the players that will still be standing at the end of this decade. If you want to go deeper into how to actually structure bankable hydrogen projects, how to run techno-economic feasibility, and how to model risk and returns for investors, check the link in the description to our green hydrogen project development and financing resources at reneeenergy.com. Because the era of hype is over, the era of execution has begun.